Alright, hi year 11s, this is Mr. Lim here, and this is our 8th video on calculations on empirical formula, so let's get started. Okay, so we're going to work out empirical formula and molecular formula and how to do things, and remember to save numbers on your calculator. Alright, so last video we went through the idea that the percentage composition is a way that we can show the ratio of elements. Alright, so the idea is that we started out with H2O, which is made up of 2 hydrogens, which will have a relative molar mass of 2 times 1.008, which will be equal to 2.106, right? And it's also made up of 1 oxygen, which is 1 times 16, which is equal to 16, right? That has a total of relative atomic mass of 18.016 grams per mole, right? But what that means is that those two things, this one here is as a percentage is 11.19%, and this one here is 88.81%. Okay, so that's what we did last time, where we went and we did the formula to the percentage composition. Now we're going to learn how to effectively do the percentage composition back to the formula. Okay, so effectively, if I just rewrite these over here, that's the hydrogen and that's the oxygen, 88.81%. Let's go through the idea. All right, so the percentage composition of a substance can then be used to determine the ratio of elements in a substance. Okay, so now all I start with is this information here, where I've got percentage of that and the percentage of that, and then I have to work out the formula between those two things. So let's have a look. Using the percentage of each element in a compound, we can work out the mass of each element in the compound. Okay, so what that percentage actually really just means is that it's saying, okay, it's 11.19% hydrogen, which means that if I had 100 grams of it, it would be 11.19 grams of hydrogen. Okay, and this one would be 88.81 grams of oxygen. Because remember, the oxygen and the hydrogen atoms weigh different amounts. So even though if you have twice as many hydrogen atoms, they're going to weigh much less than the oxygen atom, which is the majority of the mass there. All right. So using the mass of each element, we can work out the number of moles of each element. All right. So now that we've got the mass of each of them, because you can't work out the moles from a percentage. Now I know that, so the idea is that these two numbers are exactly the same, but remember, one is a percentage, one is a mass in 100 grams. Okay, so that these two are in the same mass, and so therefore I can work out the number of moles in them, and I can compare them against each other. So this one here is the number of moles is 11.10 mole. And this one here is 5.55 mole. Okay, so if that's just going from mass to mole, that should be fairly straightforward. Okay, now, going back to the notes, with the number of moles of each element in a compound, we can work out the ratio of each element, right, to each other. Now, the ratio of each element to each other is effectively done by dividing by the smallest amount. Okay, so what you can see there is that 11.1 and 5.55 is effectively saying that there's twice as many moles of hydrogen as there is oxygen. But to get that mathematically, what you would do is you would do, okay, 11.10 over 5.55, so I'm dividing it by the smallest, and 5 by 5 divided by 5.55, that equals 1, and this equals 2. Okay, so what you're doing is you're dividing it by the one that has the smallest number of moles, and you'll get the ratio of everything else to that smallest one, right? And that smallest one will have a ratio of 1. So what that is saying is that we have a ratio of 2 hydrogens to every 1 oxygen. Okay, and that's what we wanted to have, Using the ratio, we can work out the simplest whole number ratio, which is that 2 to 1 for that example, of elements in a compound. The simplest whole number ratio is called the empirical formula. Okay, and so this, what we would say then at the very end is that the EF is equal to H2O. because we got two H's and one O. Okay, so that's how we went from a percentage back to a ratio of elements. So let's go have a look at something else. All right, so what we needed to then look at is that I've summarized these steps. Okay, so determine the percentage of each compound, convert the percentage into mass in 100 grams, get the number of moles, select the element with the lowest number of moles and divide all other numbers of moles by that lowest number to get the ratio. And then this is pretty tricky here. If any produce a ratio which is an improper fraction, then multiply all elemental values by that denominator of the improper fraction. And we'll get to that in a moment. Right, so let's have a look at this first example. Substance containing carbon and hydrogen is composed of that much percent carbon and that much percent hydrogen. Determine the empirical formula. Right, so what you'll be looking at then is something like this. So I always recommend that when we do these empirical formula calculations, we turn it into some sort of table. Okay, so I would say that, okay, here's my table. I have carbon and I have hydrogen. Got a little line in the middle to demarcate them. All right, and the first thing we need to do is work out the percentage of each compound. Now, you can sometimes skip this step if you're given information that's further down on this list. Okay, if you're given information further down on that list, then you don't have to go to this percentage, but generally it's given to you as a percentage. All right, and so we say that, okay, it's 74.87 carbon and 25.13% hydrogen. Now really make sure that you get the right element for the right percentage, right? Because that's one of the most common mistakes, is that you just pick the wrong element when you look at the percentage. Okay, so the next thing there is that we want to get the mass. Now generally it has to be the mass in a standard amount. So if it was the mass of carbon in 5 grams and the mass of hydrogen in 5 grams, that'd be fine. But if you had the mass of carbon in 10 grams and the mass of hydrogen in 5 grams, that would not be fine. So as long as the mass is in equal amounts, then that's perfectly fine, but it has to be equal. Right, and so for this example, because we started off with percentages, we're going to get the mass in 100 grams. And the mass in 100 grams just happens to be that percentage. Okay, so mass in 100 grams or mass in some value, right, as long as it applies to to all of the elements to that value. Right, so now we've got the mass. We can work out then the number of moles of each element, which happens to be 6.23 over here, and I'm saving my value as A, and 24.93 over here, which I'm saving this value as B. Right, so then what I'm going to do is divide it by the smallest, and divided by the smallest is the 6.23. So this 6.23 over 6.23 is going to be 1, and the 24.93 divided by 6.23 is going to be 4. Okay, so the empirical formula then of this substance is, empirical formula is equal to CH4. That's the simplest whole number ratio of that particular substance. All right, and so that's very likely to be methane. Let's have a look at the next one. Okay, so again, we've just got a different amount of iron and oxygen this time, so let's go work out its empirical formula. So again, draw out a table, Fe and O. First thing we want, okay, what have we got? We've got the percentage of each, so we're going to put in the percentage, 69.94 and 30.06%. Again, you get the mass in a standard amount, which happens to be 100 grams here, but it could be actually any value. All right, there's my mass in 100 grams. So now that I have that, I can work out the number of moles in that 100 grams. Okay, and so the number of moles here would be 1.25 and 1.88. I'm going to save those values as B and A. Right, and then I'm going to divide by the smallest. Okay, and this one's going to be 1 because it's a smaller one. And this one here is going to be 1.5. Okay, so when you divide this by the smallest, sometimes you're going to get a improper fraction, or like a 1 point something or 2 point something, where it's not near or very near a whole number. All right, so like 1.01 doesn't really count. But if you've got like 1.5, then that's totally off, right? Or totally far from the thing. So this is where we come to that last step in here. So if any produce a ratio, which is an improper fraction, then multiply all elements values by the denominator of that improper fraction. So 1.5 isn't actually technically an improper fraction, but it would translate to 3 over 2. Okay, so 1.5 is the same thing as saying 3 over 2. And what we're going to do is we're going to take that denominator and multiply everything by that denominator. So it's 2 ions and 3 oxygens. All right, and that's the simplest whole number ratio. So the empirical formula of that substance there is Fe2O3. Okay, so that's that one there. Let's have a look at the next one. Okay, so here's a couple of practice questions for you. You can pause the video if you want to do this on your own. Okay, if you have a look at this, you can see the remainder oxygen or the remainder hydrogen. You just do 100, subtract all the others. Okay, and then you get the percentage of the remainder. Okay, and you can have a look. That's the empirical formula, right? And then this one here, again, you've got an improper fraction when you divide by the smallest, which translates to this value, and therefore you can get the molecular formula. Okay, well, not the molecular formula, the empirical formula. Okay, so just what you're looking for is that when you get to this stage here, the divide by the smallest, and you get one of these values, okay, these are all effectively the fraction parts of something. Okay, so this one here, the first one you would times by 2, this next one you would times by 3 because these are thirds, okay, and this one you would times by 4, right? It's very rare that you'll find a 0.2 or something like that, but it does occur, so you have to also know that that's a possibility. All right, next, so the empirical formula is the simplest whole number ratio of elements, so that's what we just solved. But sometimes it does not represent the actual molecular formula. Okay, so for example, C6H6 has an empirical formula of CH. Okay, and some molecules can even have the same empirical formula, like C2H4 and C4H8 have the same empirical formula of CH2. So empirical formula is useful, but it doesn't represent the actual molecular formula of substance. To work out the molecular formula, you have to have the empirical formula, so you've got to solve for that empirical formula first, and you need the molar mass of the compound. Okay, so that molar mass can be gathered. You can get the molar mass. The molar mass of that substance, or RAM, is sometimes given to you just as a number, but sometimes it's given to you as mass and moles. And so if you remember, what the big M is going to be equal to mass divided by the number of moles. So you need those two things. Sometimes it'll come up, right? And so the RAM of the compound will be the same multiple for the empirical formula RAM, which is what we were just talking about the last one here, or at least that they have the same empirical formula. Okay, so now what I was saying is that the RAM of the compound will be some multiple of the empirical formula relative atomic mass. So C2H4 has the empirical formula of this, but C2H4 is double the empirical formula. But C4H8, which is again has the empirical formula of CH2, is quadruple the empirical formula. So it's some sort of multiple of the empirical formula, right? And we're going to use that to our advantage. So if you can get the molar mass of a substance and the empirical formula, you can work out what that molecular formula is. Okay, so let's have a look. What you got? So in this question here, it's 85% carbon and the remainder is hydrogen. So let's work out that remainder. So that remainder will be 100 take away 85.63, which happens to be like 14.37. All right, but let's go do this and let's work out this. So carbon and hydrogen, we're drawing our little table. The first thing we got is percentages. Okay, so we got 85.63 and 14.37. Okay, percentages. Right. Once you've worked out the percentages, we can work out the mass in 100 grams, which will be the same value. Okay, and then we can work out the number of moles in 100 grams, which would be 7.13 moles of that and 14.26 moles of that. Okay, and so if you divide by the smallest, which will be the 7.13, you'll just get one value here and a 2 value here. Okay, now that's just the first part. That's getting the empirical formula. Now we have to get the molar mass from the question, which happens to be over where? Here. Okay, that's the molar mass. So therefore we need to go do something with that. So what we're going to do is we're going to take that the ratio of the formula to the actual molecular formula is going to be equal to the, what am I looking at? The 28.052, right, is the relative atomic mass of all of the stuff, right? And then the relative atomic mass, or the the RAM of the empirical formula is going to be equal to 14.026, which happens to be 2, right? And so therefore, that's the ratio, that's the multiplier, that's the factor that the empirical formula and the molecular formula are separated. So therefore, the molecular formula is equal to the empirical formula times 2 on 1, which happens to be C4H8. Okay, so that is how you would work that one out. All right, let's have a look at the next one. Okay, so substance is 79.89 carbon, the remainder hydrogen, molecular mass of that, determine the empirical formula and the molecular formula. Okay, so what you got? So carbon, hydrogen, okay. So what we're going to start off with is with the percentage. So this is going to be 79.8, 0.89, and the remainder hydrogen, which would make it like 20.11 or 20.11. Okay, once you have that, you can work out the mass in 100 grams, which happens to be 6.65 for you and 19.95 for you. Okay, so now that I've got those two, I can go divide by the smaller. Oh no, wait, I have to get that into. Oops, that was the number of moles. So that should have been down here, and then this one here should have been something like mass of animals and stuff like that. Okay, but this one here, we've got the number of moles, and so therefore we can work out we divided by the smallest, which happens to be the carbon one, which means that one's 1 and the hydrogen is 3. Okay, so now that we've got the empirical formula out the way, we can go start on the new stuff. Empirical formula, CH3. Okay, so how do we get the molecular formula here? What we're going to do is we're going to work out the molecular formula of the substance, because we don't know what it is yet. Okay, which is 30.068, and then we have to get the molecular formula or the molar mass of the empirical formula, right, which happens to be the 15.034. Okay, so that is the two values, so then I can work out the ratio between them will be equal to the molar mass of the substance over the molar mass of the empirical formula, which will be equal to 30 over 15, which will be equal to 2. All right, so that's the ratio there between the carbon and the hydrogen. So the empirical formula is equal to CH3, but the molecular formula will be 2 times that, so therefore it's going to be C2H6, which is your ethane molecule. All right, and if you want a couple more examples to have a go, so you have a go at these ones, and then go show you the answers there. All right, so that's all for empirical formula. One more video to go. Adios.